All right, this is problem 1440. It's on page 613. A small ball A is dropped from a height h onto a rigid frictionless plate at B and bounces to point C at the same elevation as B. So let me sketch the system so you can see what's going on. I'm going to need a little bit of space here, so I'll make it relatively large. Here's point B where the ball drops. The ball drops a height h. The angle of the plate, theta, is here. Anyway, the ball comes down, it bounces over to C, where C is supposed to be at the same elevation as B. Now the distance that it travels, d, is this horizontal distance. Okay, now they've given us some information. They've told us that the angle of the plate is 20 degrees. They've told us something important about the plate, that it is frictionless. And they've told us that the coefficient of restitution is 40%. Okay, and we're supposed to determine distance d. So let's see if we can solve this. Now, the nice thing about this is that once we're done solving this, I think we're going to find something interesting. Then we'll get to test it. Because I've got some ping pong balls, and we can take a book, prop it up, drop some ping pong balls, and see if what we find with this problem is really true. So let's see. You guys have already worked an example problem, so what do you think the first thing I should do is? Probably use potential energy, right? Well, how fast is the thing moving when it hits the plate? That's important. So let's get that out of the way. Now the height h, I've forgotten, did they give that to us? Let's see. No, they didn't give us the height h. Okay. And they didn't give it to us in the figure. All right. So the velocity, how do we get it? Well, you guys hopefully have just gone through and you've used the energy equation. What did you find? The velocity is the square root of how much? You just did this. 2gh. We don't know the height, but that's okay. Right? Because this should be the velocity. Okay, now what is that? Well, that's the velocity of the ball before it hits the plate. Now the plate is rigid. The plate's not going to move. The plate's velocity before impact, during, and after impact is all 0. Right? So couldn't we just do this? Couldn't we say, well, the coefficient of restitution is the relative velocity after impact divided by the relative velocity before impact. So that would be the velocity of the ball. And let me call this the plate P and the ball B. So the velocity of the ball less the velocity of the plate, and this is final, divided by the negative velocity of the ball initial minus the velocity of the plate initial. We know the plate is not moving before or after impact, and so we could just say this is the velocity of the ball final over the negative of the velocity of the ball initial, which kind of makes some sense, right? Because the ball is going to be moving in sort of the opposite direction, but it doesn't completely make sense, right? Because the velocity of the ball initial is just straight down. The velocity of the ball final is at an angle. We know that's going to be the case just from our everyday experience. So what's wrong here? Well, what's wrong is that I'm not analyzing this correctly. I've gone from central impact to oblique impact. Notice that the impact occurs at an angle. And the fact that this plate is frictionless means that that plate can only apply an impulsive force in this direction. Right? It's frictionless. It cannot apply any force up or down the plate. Therefore, it's not a surprise that the ball bounces off with some x component that it didn't have before. Okay? Now let's expand this a little bit. We're not done with our equations yet, because really this v is not this v. That's why I didn't write them with the same subscripts. This v is this velocity. This v is a component of that velocity. Okay, so we have to analyze it. In fact, it will be helpful to look at this plate with a rotated coordinate system. So x is here, y is now here. And so the velocity that the ball comes in with is here. Now, remember that when we talk about impulse, we write the impulse momentum equation as mv plus integral force over time equals mv. This is before, so initial. This is after, final. We have to write this in a direction, right? The only direction that makes any sense here is the y direction. Why? Because this plate cannot apply any impulsive force except in the y direction. We've already said that. It can't apply any friction. So basically what that means is that the momentum of the ball in the x direction is conserved. Why? Because there's no force applied in the x direction. During impact, no force is applied to the ball in the x direction. Therefore, the ball's velocity in the x direction remains constant. You could write it as a trivial equation, but it looks like this. Right? It says the initial velocity in the x direction of the ball equals the final velocity of in the x direction of the ball. Okay? All right. So you can probably smell a cosine and sine coming now, can't you? Right? Okay, so let's do some conversions. All right, I can get rid of this now because we're done with the figure, at least for the time being. You've got it there in front of you in the book, so hopefully we don't need it. But let's go ahead and break this velocity up. Now, if the velocity is coming down like this, if I took a normal up off the surface, hopefully you could figure out that your angle theta is right there. Okay? So if that's the angle theta, and I want to break up this velocity into two components, there's Vx, and I won't write initial or final, they are the same thing. And here is V initial y. So far so good? Yeah.
Okay. I was looking back over the problem, and D depends on H. So will we just get an answer?
That's a good question. Will we get an answer in terms of H? Let's find out.
Yeah.
Good question. They didn't give us H. So it's like, why didn't they give us H? Won't that? I mean, it seems like the higher you drop the ball, the farther it goes.
Yeah.
Let's find out. Good question. Let's find out. And please, if you have a question like that, please ask, because I love intuition questions. They're really good. Because one of the main goal, in my opinion, of this class is to sharpen your intuition. So this is very good. Anything else before we continue? Okay, so help me write down the velocity in the x direction. Would I use sine or cosine? It's going to be equal to V times what? Sine?
Cosine.
How many people say sine? How many people say cosine? Okay, good, it's sine. Because look, it's this length which is opposite the angle, right? Okay, here's the hypotenuse we're trying to break up. It's opposite the angle, so we need to use sine. How about Vy? We have to be a little bit careful here because Vy actually has a negative component. So it's not just V cosine theta, it's negative V cosine theta. Okay? We have to be a little bit more particular in this chapter with our directions than we did in chapter 13. Okay? So Vy, and I'm not being very careful here, what I've called Viy, before impact. Now, unfortunately, again, I haven't been very consistent because VIY would also be VB initial because that's the velocity of the ball that the coefficient of restitution has something to say about. The coefficient of restitution has nothing to say about the x direction. There's no change in the x direction. It only will relate to the y direction. And so, really, this is VIY. Of course, we're just talking about the ball. And so now you see that it's pretty easy to come up with the Fy. That's really just this right here, right? Just rearrange the equation. Vfy would be equal to negative EVIY. Now, E is not the special number E on your calculator, not 2.7, whatever it is. Okay, E is just the coefficient of restitution, which is 40%. Okay, so VFY would be VIY times negative E, but that's negative V cos theta, negative E. Of course, the two negatives are going to go away, so can I just put the E over here and call it done? Is that okay? Now, I'm working at symbols. One of the reasons I work this problem is because I have to use symbols to go, well, you don't have to. It's easiest to use symbols to go through it. And I know you guys are uncomfortable with it. I'm not doing it to make you feel uncomfortable. I'm doing it to try and convince you to start working with symbols. It'll be much more effective for you. If you never get to the point where you can do anything besides plug in numbers, you're really going to struggle in this class. So try to transition to symbols. I know it's uncomfortable. You'll get used to it. It's okay. So basically, we've used up this equation, right? We've used up the coefficient of restitution equation. Okay. Now, I'd like to know what happens when the ball bounces off. I'd like to know how it goes away. What happens here? Well, I already know, don't I? I know the final velocity in the y direction and the final velocity in the x direction. Notice they are both positive. So the ball's going to come off the plate at farther than 90 degrees. I know that because look, these two are both, well, these two are both positive things. Okay? Now, basically what I have here is two velocities in a rotating coordinate system. I'd like to rotate them back, right? I'd rather go to a coordinate system like this. Let me call this the y prime, x prime coordinate system. Okay, why would I want to do that? Well, because I want to analyze motion in the x prime direction. Okay, so now, hopefully you won't get too confused here. What I'm going to do is transform both the vectors. Let me show you. So I'm going to take Vx, and I'm going to draw it right here. There's Vx, right? What's the angle here? 20 degrees. So, could I get a component of velocity? We'll need that in a second, but I think we can remember it. Could I get a component of velocity in the x prime direction from Vx? Sure, it has a piece, doesn't it, right? In fact, its piece would be Vx multiplied by cosine theta. You see what I just did there? All I did is I computed that length. That's all I did, right? But the velocity in the x prime direction has a contribution from the y velocity, because look, the y velocity is like that, right? So it contributes in the x direction as well. In fact, its contribution looks like that. Now, how would I get the magnitude of this piece? With sine, exactly. So I need plus Vfy sine theta. Y final, well, x initial and final is the same, so I just dropped it off. But really, it's the final velocity. This is also the final. Okay. Now, let's expand this just a little bit. Vx is actually V sine theta. So that's Vx. I have to pull down the cosine theta. Vfy is E V cos theta. I have to pull down the sine theta. Okay? And now I've got the velocity in the x prime direction. Notice this is after impact. How do I know it's after impact? Well, I'm using Vx and Vy that are after impact, so this must be after impact. All I'm doing is changing the vector to a different coordinate system. I'm just writing the x prime component of velocity after impact. Okay, now I'm going to ask you for a little bit more help with Vy prime. So this again is after impact. How would I write it? I need the y component of Vx. What would that be? Negative Vx sine. Right? Good. How about Vy? What does it contribute to Vy prime? Positive Vy or Vfy cosine theta. Right? Okay. Now let's plug in Vx. Vx is simply V sine theta, and I get another sine theta from up here, and the negative sign just comes down. Plus Vfy is E V cosine theta, the cosine theta comes down. Okay? And then what? Well, this is negative v sine squared theta plus e v cosine squared theta. Okay? And now I have written the velocity after impact in the x prime and y prime directions. Okay? You still alive? Barely breathing? Okay. All right. Now, let's see. Yeah, I've used the, I didn't really need to use the momentum equation in the y direction. Instead, I used the coefficient of restitution to find VFY. If we wanted to, we could go back and find the impulse, but that's not something we were asked for. So we'll just get rid of this piece. We're done with this bit here. And really, we've used this as well. So hopefully we haven't made any mistakes, right? Because if we have, I've erased all the mistakes. I can't go back and find it. And we'll just get to the end and be clueless about what went wrong. But hopefully everything's okay. All right, now, the real question is, how much distance is accomplished? Remember that where the ball bounces and where it lands are at the same elevation, right? So what forces act on the ball to pull it back down as it's in flight? Gravity, right? So gravity basically determines how much time the ball is in the air. Does that make sense? So basically what I'm saying is we can use the constant acceleration equations in the y prime direction. Let me not forget that I have a y prime, x prime coordinate system that I'm working with. Okay? Now, of course, we could make the substitution at this point, get rid of v in lieu of root 2gh, but we'll wait for a little bit to see what happens. Now, what we want to do is solve for the distance that the thing travels. Now, obviously, the x prime direction of velocity will remain constant, right? There are no forces in the x direction, so the ball will simply maintain its x component of velocity constant. But the y component of velocity will change. In fact, the y component of velocity we expect to be positive initially, right? And then end up negative at the end. But what we're really interested in, excuse me, sorry. What we're really interested in is the ball's flight time. That's what we really need. Because if we knew that, then the distance d that we're looking for would simply be vx prime times t. Does that make sense? In other words, if you're moving down the road at 50 miles an hour and you move for 1 hour, you're going to move 50 miles. Right? So if we're moving down the road at constant speed, multiply that by the amount of time that we move, and that'll be the distance that we move. So we really want to get at this time, this flight time, but that will be determined by the y prime direction motion. Okay? So let's go back to chapter 11, and let's just write down the constant acceleration equations and see which one we might want to use. So help me out. You guys should know this. You've got an exam coming up next week, right? So you know this by heart already, right? Okay, well, this is kind of a little bit of exam review then. All right, so let's write a y position equation. I will start off with y equals y naught plus what? How does the constant acceleration equation go?
V naught t.
V naught y, good, t, yes, plus?
At.
Well, how about 1/2 at squared? Okay, that is one of the constant acceleration equations. Now, would this be useful to us? That actually may be quite useful. But let's see if there's anything that's easier to use. We may as well write down the other equations as well. Okay. So what other equations are there? Well, there's v equals what?
V naught.
V naught.
Plus at.
And let's write vy, so v naught y. Okay, plus what?
At.
Plus at. So we need a y t. I should have put a y here since we're writing a y component equation. Okay. All right. What else?
Vy minus, or Vy squared minus.
Vy squared equals
Equals V naught squared.
v naught y squared plus
2a delta y.
2ay delta y. That's right. Okay, these are the three constant acceleration equations that may be useful to us. Will this one be useful to us? It doesn't have time in it. We really want to get time out of it, so probably not. Will this one be useful to us? Well, this one has time squared. If I can avoid it, I will. right? Because I know I'll end up with a quadratic to solve. What about this one? Will this help us? Well, Vy would be Vy prime, right? To apply it to our particular coordinate system. Or excuse me, I'm sorry. V naught y would be Vy prime. What would be Vy? In other words, when the ball comes and hits the plate, what would the velocity in the y direction be? No, that's after it hits. Before it hits, what would the velocity be? It'd be equal and opposite, wouldn't it? Because if it came up with a certain speed as it came off the plate, it's going to come down with that same speed, right? So these two would just be opposites of each other. So what does this tell us? Let's try to use this equation and see if we can save some time. Vy after impact. So this is after we've reached point D. Let's just say, or just before we reach D. It will be equal to the negative of Vy prime. And in fact, V naught y will be Vy prime. All I'm saying here is that when the ball bounces off in the y prime direction, it's going to have a certain speed. When it reaches D, it's going to have the negative of that speed. Right? I mean, it just makes sense. So, what could I do to simplify this equation? Well, like I said, we're not going to use this one. Let's work with this a little bit. If I move this term to the other side, I would have Vy less V naught y equals a yt. So Vy, and these will be in the y prime direction. Now I'm getting confused. V naught y, I know this one's going to be Vy prime, and this one is going to be negative Vy prime. So what do I get? Well, I get negative 2 Vy prime equals ayt. And it looks like I've got a problem, right? Because Vy prime, I know, is going to be a positive thing. We've already talked about that because it comes up off the angled plate, right? So it must be positive. And yet I've got a negative sign here that almost indicates the time is going to be negative. Did we figure out a way of time travel? Can we now go back in time by bouncing balls off of plates?
Yes.
Yes, we did it. No, actually, ay is just negative g, right? Because y prime is up, g is down, and the acceleration in the y prime direction is in fact down. So this is just negative g. Okay, so in fact, we can use that simple equation. We won't have to go through the quadratic equation. You could if you wanted to, but you don't have to. And what you'll find is that t, sorry, I'm going all over the place.
I have a question.
Yeah, sure.
What is that? Vyd?
This is the velocity in the y direction just before it's reached point D, that distance we're looking for,
Okay.
which is going to be a negative thing. Okay, so the time that it takes to get there from this equation down here would just be negative 2 Vy prime over negative g. So obviously the two negative signs go away, and there's the amount of time that it takes. So we can plug that in then for the distance d. It would be Vx prime from here multiplied by Vy prime times 2 over g. Okay, now finally, we can plug in Vx prime and Vy prime from up here and see what we get. Okay, so let's see, is there any way to simplify this a little bit? I don't think so, unfortunately. So we've got a little bit of a mess on our hands. I'm done with this over here, so let me transition over here and plug all this in and see what we get. Okay, so d equals 2 over g, that's the easy part. I need Vx prime, that's going to be v. In fact, you know what, let's factor out the v. Let's pull the v out, because notice it's a common term here. And we would have sine theta cosine theta plus e cosine theta sine theta. But notice the sine theta cosine theta term is the same, so I could factor it out as well. So let me modify this one more time. The sine theta cosine theta times 1 plus e. You see how what I've written here is Vx prime? Now I need to multiply Vy prime. Vy prime is this. So once again, the v will come out. Okay, so I'll have v, takes care of that bit. Then I will have negative sine squared theta plus e cosine squared theta. I'm just out of room. separate those off. Okay, so that's Vy prime. If you see a mistake, please say something. I think we're okay so far. Well, let's simplify this just a little bit. The two V's can go together. I have 2 over G V squared. And notice that the V is root 2GH, so this would just be 2GH, right? Sine theta cosine theta times 1 plus E times negative sine squared theta plus E cosine squared theta. Now I'm wishing that I had written out the solution ahead of time to make sure I don't make any mistakes. But we are here, so let's continue. Notice the G cancels out. Interesting that the acceleration of gravity cancels out. And now I have to actually FOIL this, right? I have to actually do it. So let's try it. This is 4H sine theta cosine theta times, well, let's see. 1 times each of these will be negative sine squared theta plus E cosine squared theta. That takes care of 1 times this. And then I have to multiply E by these things. So minus E sine squared theta, let's see, plus E squared cosine squared of theta. Okay? This E times E is E squared, so that should be it. Now, let's see. There's got to be a simplification here, but I'm not seeing it. Yeah. We can plug in the numbers and find out, right? So we've got theta, we've got E. Plug this mess in your calculator, please, and let's see if it comes up to something nice and simple. I think it may. So negative sine squared theta plus E cosine squared theta minus E sine squared theta plus E squared cosine squared theta. What do we get?
I don't know how to do sine squared in the calculator.
Oh, you take sine of the angle and then square it.
Oh, okay.
I was hoping that there'd be a sine squared plus cosine squared, which you pull out, because sine squared plus cosine squared is 1.
Sorry, where you factored out sine times cosine from the V's applied from here.
This, is that what you're asking about?
Yeah.
That came from here,
Oh.
from Vx prime. Good question. So whenever you get a number for this, please let me know. If you're working this on the video, then you should do it too. I think I'll pause the video till we get a result. So to finish off the video, what we've done is we've calculated the numbers for all the constants and multiplied it by h. And we noticed the h did not disappear. So basically the distance b is almost 3/4 of h. Now what we're going to do, and one thing you may want to do if you're home watching the video, is we're going to grab some ping pong balls, bounce them off the books, measure their heights and how far out they go, see if this is reasonable. Okay?